back, and the next section is about sanitizers. So the LLVM sanitizers are again a suite of debugging tools for detecting various kinds of bugs. There are many. Their sanitizer is probably the most popular one: leak sanitizer, thread sanitizer, memory sanitizer, and goes on and on. And these tools are only for C and C++ codes here. And there are a few very interesting documentation in the Clang site and GitHub, Google's sanitizer pages. There are a lot of information out there. And first, the supported compilers. So sanitizers can be used with more than just LLVM compilers. And they are actually compatible with all compilers on Palmera except the NVIDIA compiler. So you cannot use the sanitizers with NVIDIA compiler. And another nice thing is that these compilers, GNU compiler, Cray compiler, Intel compiler, etc., they accept the same LLVM sanitizer compiler flag. So this is nice. For MPI codes, what that means is that we can use the Cray compiler wrappers, as usual, CC for C code and the capital CC for C++ codes. For non-MPI codes, if you want, you can use the basic base compilers like a GNU, GCC, G++, Cray, CC, Cray CXX, Intel, ICX, ICPX, the new compilers, new Intel compilers. For AOCC, it's Clang, Clang++. We have our own LLVM program environment, plugin. The commands are the same, Clang and Clang++. And Intel's old C and the C++ compilers, ICC and ICPC, don't work for sanitizers because they are not based on the LLVM Clang-based compilers. So to build the sanitizers, previously I mentioned that the Valgrind, the tools instrument the executable at the runtime. But this one, you have to instrument during the compile time. So you have to build using the special compile flag, sanitizer equals something. And then the executable runs really slow, several times slower, and it uses a lot more memory. So it is very important to rebuild your code after debugging without the sanitizer flag. Otherwise, your code will run too slow. Again, this instrumentation is done during the compile time. So that is why. For the Valgrind, you can probably use it for the production code. If you did not include the optimization level, then you can do it. But in this case, you have to rebuild it. This is very important. So audio sanitizer, this detects many memory errors. So like use after free, you free it, but you try to use it again. So that is the pointer that is pointing to the previous allocated memory block is called a dangling pointer at this point. Or you can also detect the out of bounds array references to heap, stack, and the global variables. And can detect the use after return. You try to use the stack object that was defined in the function after you return from the function. And the similar thing, use after scope, if you're out of a certain scope and you try to use some stack object that was defined in the scope, then this tool can detect that as well. Again, this one, so another thing is the initialization of the bug. This is if your code is such that there's a non-deterministic output, regarding the initialization between the constructors in different source file, then you get a different errors because of this non-deterministic nature. So these other sanitizers can detect that as well. Double free and the invalid free, also you can detect the memory leaks. So I'm not sure how we pronounce ASAN or ASAN uses an extra memory blocks, just like the Valgrind. And this time it is called the shadow bytes, okay, for tracking the state of allocated memory block. And one shadow byte in ASAN represents 8 application bytes. So one byte covers the eight bytes in the data block, in the application. So for x86-64 architecture, they follow this formula, shadow the memory address for shadow bytes given by this formula. So for the shadow byte, if it is indicated as 00, shadow byte is the 16-bit, 8-bit, the 8 bits, right? 8 bits, 1 byte is 8 bits, so we can represent as 2 hexadecimal digits, so 002 FF. So if 00 means that all 8 bytes are addressable. They can be written or they can be read. So if it is 01, 02, 07, that means that only partially, some of the bytes are accessible, not all. So FA means that heap left zone. So apparently they use the red zone. This is the common technique used by the many debuggers. They actually paint using the certain bit pattern for the certain area outside the memory block, so that if that area, that area is the value got changed, you know that the memory corruption there. So this is a typical way of detecting memory error by many debuggers. So they do the same thing. They put a red zone, heap left. Apparently, it's the left side of the memory block that was allocated. But the direction is a little confused, left and right. But anyway, the important thing is the red zone. You shouldn't be touched, right? FD is when the memory block was freed, then it is marked as FD, etc. So ASAN uses these shadow bytes to detect illegal memory usage here. The examples in the next slides. So the first example is illegal memory access. Here again, we allocated a 10 integer array, so 40 bytes memory block, but it tries to access the 11th element here, right? So illegal memory access. So compile with the fsanitizer equal address, compile it. When you run it, then we get this output here. It's quite complicated, but you can group 3 here. The first one reports the heap buffer overflow. It was trying to access the 11th element, which is non-existent on address here, and that is called at line 7 of this function, this source code. This shows the back traces, and by the way, the memory block is for the 40 byte region. From this, the left side included, and the right side not included. Round parenthesis, this square bracket here, right? And using this, and the bottom part is about the shadow bytes. So this one using the previous formula here. Sorry, let's get back. This formula, shadow, whatever. We can tell that this can be mapped to this and that here. And then, so what it means is 8002, here is 8000. So 8001 is here, 8002 is here, so yes. It starts from A002, and there are 5 double zeros here. So each double zero means that 8 bytes here, right? So 5 times 8 is 40 bytes. So this is the memory block that was allocated in the source code here. And then next, there's a square bracket here. So what that means that there's illegal attempt to access that the memory block associated with this shadow byte here. By the way, the shadow byte value is FA. That means that is in the red zone. So it was trying to write something in the red zone. So it raised a flag. So that's how it detects the error. But anyway, that's strange because this is the right side of the allocation. So maybe hit right red zone, but I'm not really sure. It doesn't care. I don't care. Anyway, the important thing is that this is a red zone, right? FA. So this is how the ASAN detects error. So leak sanitizers, the another sanitizer, this one detects memory leaks. Again, here, pointer, using this pointer, we allocate the 7 bytes of memory, right? And then without freeing this one, we set the value to null, 0, right? So the memory block allocated, 7 byte memory block allocated previously cannot be accessible anymore, right? Because this pointer, which was accessible to that the memory block, the only accessible memory, the pointer that can access the memory block, now is pointed to something else. Its value is null. So we lost the 7 byte memory. So memory leak happened here. So we build it using this fsanitizer leak. Then if we run it, then it correctly reports the 7 byte memory got leaked here, right? And another thing is that this leak sanitizer, which only detects the memory leaks, can be combined with the other sanitizer. So you can run under other sanitizer this functionality. And by using the other sanitizer, then it can be used for the memory leaks and other memory errors as well. So you compile with the other sanitizer for other sanitizer, and then you use this environment variable setting here. So it detects underscore leak equals 1 for this run. We are using this environment variable only for this run here. Then it shows that the memory leak happened, 7 byte loss, etc. Right? And the another sanitizer called the memory sanitizer, MSAN. This is to detect the uninitialized variable. So again, if uninitialized variable is used, then you can raise a flag. So to use this tool, you compile with fsanitizer memory. So for better performance, you use a -01 flag, because it doesn't matter whether it is the 00. It's still the high optimization code can still run into the same error. So we can use the -01 to run faster. But the important thing here is that the GNU compilers don't support MSAN, as far as I know. And if we use the Cray program or Intake program, the source lines are missing in the output. So a workaround is to define this environment variable. So if you want to see that where the errors occur, and we heard from HP that this is fixed in the later release. So this is the example. So this UMR.cc, again, this one is it has 11 it allocates a memory block for 10 integers, but it only initializes just one element. There are six element here. So when you call this function like that, then RJC number of arguments is 1 here. So that value is undefined. So in this if conditional here. So again, we compile with the fsanitizer equals memory. When you run it, it reports the use of an uninitialized value. So thread sanitizer is to detect the thread race condition. What is the race condition? So when the multiple threads are allowed to access the same memory location simultaneously, and then one of them is to write that location, then order of operation among threads are important, and that they can affect the numerical result. So this is about, I mean, if you don't correctly specify the order, then this is a coding error. So TSAN can detect the race condition. You compile with fsanitizer equals thread. Again, for better performance, you just -O or higher. And because of thread condition, the race condition, you cannot always detect the error. I mean, the tool cannot always detect the error. Sometimes it doesn't, it fails to detect because of race condition. Sometimes it detects the error. So you may have to run a few times with the thread sanitizer here. So this is a buggy code. This is a buggy OpenMP code, parallel. Everything looks good, except that it doesn't have a reduction clause for some. So in other words, the older threads are, free to write this one. So this will be basically, can have a garbage value as a result. So there is the race condition because there is no predetermined order of modifying this variable, single variable here, right? So we compile with the fsanitizer equals thread and run it. Yes, it reports that the one thread T1 was trying to read the 4 bytes, while the main thread, probably T0, I don't know how that the numbering goes, but that one tries to write it. So there's the race condition detected. So this is how this T1 was created, some background information. But anyway, you can detect the thread race condition like this. And then there's also like the Valgrind for HPC. We have a sanitizer for HPC. This is HP tool for MPI code that can merge sanitize output so that we can parse output more easily. They group basically output with the same backtraces or, anyway, so it presents the sanitizer result by global MPI ranks sharing the same backtraces here. So the sanitizer for HPC currently supports only these 3 LLVM sanitizers: butter sanitizer, big sanitizer, thread sanitizer, and in addition to that, it works with the NVIDIA's compute sanitizers memcheck. I'm not sure if you are familiar with that. The NVIDIA has 2 types of big debuggers. One is a CUDA GDB, and the other one is a CUDA memcheck, previously known as CUDA memcheck. Now they rebranded it as a compute sanitizer. And this is also a suite of the debugging tools, like memcheck is one of them. Initcheck, that is to check whether the variables are initialized, and the race check, there's the race condition, etc. So it works only with the sanitizer memcheck. I shouldn't say only, but it works with the sanitizer memcheck. But we saw that the aggregation, I mean, the report, the sanitizer report by group MPI ranks are not perfect. So we filed a bug report with the HP, and they report that this problem are getting fixed. So here, this is how to run the Sanitizers4hp modulo this Sanitizers4hp and run I'm sorry. Where am I? I'm sorry. Sanitizers4hp and then option and the double dash, and then after the double dash you put out the application that you run. Here, some popular options is -L option, that is to specify the how many MPI ranks and how they are launched, like N C value and the CPU bind, and of course these flags go here, right? And -F, we'll be using this one for the last one. It basically assumes that the executable instrument by LLVM Clang sanitizers, but this one supports the CUDA compute sanitizer, right? Which is not the instrumented with the LLVM sanitizer. So for that case, this flag allows to bypass the Clang sanitizer check. So -N is to bypass MPI. I don't know why that is and what the use is, but also we can provide some ASAN, LSAN, TSAN options, something like that. So this is a CPU code example with the Sanitizers4hp. This buggy reduction code. It is we turn it into MPI code by just wrapping with MPI init, MPI finalize, right? MPI init, and so it's very similar to the buggy reduction code that we saw. There's buggy reduction on the OMP, but this is MPI OMP. Here we wrap it, and this one the same thing without the reduction clause. So there is a race condition, and we compile with the thread using now this time using the CHP Cray compiler wrapper. Okay, and then you start the interactive job. You load this module. You set the OMP num threads, and then run sanitizer like that, and then it reports this. As I said, that the aggregation of output is not perfect at this moment. The reason why I'm showing is that I want to show that the how to run this thing, even though that the current way of using this tool generate not correct, incorrect results. Actually, they should be grouped as one, ranks 0-1, and they report the same single group of MPI rank, not two. So again, that we filed a bug report, and that this is getting fixed. So this is a GPU code example. So this is CUDA code that we found in the NVIDIA compute sanitizers. There's some example codes for that tool available. So we got it, and we just added again embarrassingly parallel MPI wrapping here. So it's we compile this using the MVCC compiler, NVIDIA's, and then we link using CC. And then this is how we run the GPU code, SLL, the interactive job. We modulo the Sanitizer4hp module, and the Sanitizer4hp, and we provide the launch arguments, -N4, 4 ranks, and separated by the 32 CPUs. We use a CPU bind 2 cores, GPU per task. Each task has 1 GPU. GPUs per task equals 1, and the GPU bind is none. And we have to specify the compute sanitizer path this way, -N, and then the -F to bypass the requirement that the executable is instrumented with LLVM sanitizer, which, I mean, this executable is not, right? So we have to use -f here. And then dash and executable name. Again, aggregation is not perfect. This is embarrassing parallel code. We should see a single group of MPI group, right? Single MPI group, but it's split into two. But again, the point is that we are not saying that this bug, and what I'm saying that when this bug is fixed, you have to run this way to get the correct result. We are trying to show it this way. So for hands-on session, again, the exercise materials are on the GitHub. You clone it. You must have done that already. And then this time you go to the sanitizers directory and follow that the README MD file in each direction. Other sanitizers, this one, etc. So that's it. Do you have any questions?
From your experience, when is it better to use Valgrind and when is it better to use sanitizers?
Yeah, I don't have much experience, but yeah, sanitizers are new things here, right? And they are getting popular. And one article, online article, compare them actually. I mean, the sanitizers are more accurate. You know, they are no false positives, they say. And so, I mean, so it's good. I mean, I think that the one downside is that this is compile time instrumentation. But that article mentioned that with Valgrind, you don't have to compile. You get a certain executable, certain thing, even ls command. You can use Valgrind to see what the errors is. But you cannot do that with the sanitizer. So I think that the sanitizer is getting better. That's what I heard, and you know, but yeah, still Valgrind is a useful tool. That's what I'm thinking. Yeah. So you can probably use both if you can. And there are many sanitizers actually. We only document in our webpage only a few tools, but we are planning to add more in the future. And we are trying to learn it, but yeah. So that's my take here.
I'm not sure whether you mentioned this earlier. Can you combine different sanitizers together, or do you need to recompile for using each sanitizer one by one?
Yeah, you have to do one by one.
Okay.
Yeah. I think that this is new to some people said that Valgrind should go away, but I don't think so. The sanitizer, I mean, I find the Valgrind quite useful as well. But yeah, the sanitizer has some restriction like. So let's go to the sanitizers. There are other sanitizers. You just follow the instruction here. Again, I explained that what I explained here, what I explained before. They are mapped this way, and this is 45, etc. Sanitizer, and yeah, and the Sanitizers4hp with this GPU code. We are using this again, their tool. So this one has a couple of errors. They said one is the unaligned kernel. This is the character, this is what is that called? You make into character and +1. So this is a misalignment, right? The 4 integer should be start the 4 byte. It's a 4 byte alignment needed, but the character is 1 byte. So if you just add 1, then that can be a problem. That's what it is. I'm not really sure about this one. I think that what it does is that this is not the hit region. So that's why it is this memory address. But if somebody who knows the architecture better, then probably they can explain better. That's what it seems. But anyway, you can try this with the you follow this instruction. Just so CPU code example, I already explained what it does. Yeah, just why don't you work on the hands-on and let me know that if there's a problem or questions. Okay. Or that the CUDA directory in the GitHub. Yes, you have. This is some module. Actually, I should. You can get it from there, or you can actually, instead of git clone, you do a git clone dash recursive, and this one, and then it'll populate compute sanitizer example code. But we don't have anything for the CUDA GDB side yet. Yes, these directories are empty. Yes, but they are actually. Let me just see here. CUDA. This is empty. We know we can add a few things, few examples from our previous training. And this is a compute sanitizer, the sub module, git sub module here. And the example code was from memcheck, this code. So we modified this code slightly to make it an MPI code. Yeah, it is. So you can recursive cloning, git clone dash recursive, and this one, and then it'll populate the compute sanitizer directory. So this memory sanitizer compiler are you using the GNU compiler? GNU compiler doesn't support the memory sanitizer. Yeah. Yeah, thanks, Justin. Yeah. Right. I think that Justin is writing. Let me just go back to here. So Cray environment, you have to use this compiler name if you want to use the base compilers. There's no clang there. Yeah, Alfred. So in Cray environment, there's no clang.
Yes, thank you. I think Justin just
Okay.
answered the question.
Okay, got it. Thank you. So for instance here, we said that the one shadow byte is for 8 application bytes, but this is not the only option that is allowed. Why not 16? Why not 32 bytes, right? Or why not 4 bytes? Apparently that can be done because we have one shadow byte ranges from 0 to 00 to FF. So there are many other we can still represent this thing, but probably if we use a 16 byte, if one shadow byte represents 16 application bytes, then my concern, I don't know, my concern might be one shadow byte would cover 2 entities, 2 different, like, the last element of one array and the first element of the second array or something, but that would be already inconvenient. And this is largely to reduce the memory usage. In the Valgrind case, it was 1-to-1, 1 byte, V-bit. 1 V-bit is for one bit in the memory, but in this case, 1-to-8. But so I think that the 8 might be some good compromise. So Alfred, about the Clang in the Cray compiler environment. So again, you have to use this. I include the Clang case, Clang example, just to demonstrate that the sanitizers work over all these program environments. For AOC, I probably must have used the AOCC plugin. So PRG-EMB-AOCC, and I tried the Clang. Just to demonstrate, it's not because I want to use these compilers are important to me, but I just want to check whether that the sanitizers work with the AOCC compilers. So I tried Clang, but that doesn't mean that you have to use the Clang compiler in Cray program environment. If you're in the Cray compiler environment, then you have to use Cray CC or Cray CXX.
Fence is working now.
Okay. So I said that. Yeah, the blog that I mentioned is this. It's written by Red Hat person, and it definitely lost, and still reachable, possibly lost. This is interesting example. And what it does, why the pointer ended up as interior pointer. So they use this pointer to allocate the three elements of the norm struct. And then this code uses that pointer, which was used to allocate the initial memory block. And this code increments that pointer like this here. So it is moving from the start pointer to the inside. So it doesn't go all the way. The final number is 3, but it only reaches the third element and then program exit. That's why you got a possibly lost category memory leaks here. 24 bytes is because of associated with these nums. There are 4 integers. So 4 times 6 is 24 bytes lost. And the 48 bytes lost here is because of 3 elements of this struct here. This is pointer, so it takes 8 bytes, integer 4 bytes. So this has to be 8 byte line. This has to be 4 byte line. So they need a 4 byte padding. So 4 integers, 4 byte for integer, and 4 byte for padding, and 8 byte for pointer. So each element has 16 bytes, right? So we have 3 elements here, right? 3 elements. So 16 times 3 is 48. That's why we got a 48 bytes possibly lost. This is due to this. Anyway, the problem here is that they are using the pointer that was used for allocating the memory block, but they are incrementing the pointer in the program. That's how we got the interior pointer, etc. So, anyway, that's all. Do you have any questions? Let's wrap up the tutorial. And please fill out the survey. Okay. So please let us know if you have questions or problems. Okay. So thank you very much, everyone. If there's no more further questions, then okay, bye.